On November 14th, after several near-explosive events, Theresa's atlas came back to life in a baffling way, and James Webb announced strange signatures from within the object. From what was once just a faint anomalous speck of light beyond Jupiter's orbit, it gradually revealed itself layer by layer, an entity that brightens periodically without needing heat, radiates energy from within, while its surface remains absurdly cold, sheds parts of its structure without leaving any debris, and steers its trajectory through space with no exhaust plume, no tail, and no trace of any visible propulsion system. After a series of impacts and repeated displays of bizarre personality, 3I Atlas has increasingly lost the appearance of a natural object and begun to resemble an alien machine wrapped in layer upon layer of mystery. Up next, we will continue our journey following this cosmic visitor known as 3I Atlas, as the James Webb Space Telescope for the first time records light with artificial signatures and radio signals emerging from this entity, along with predictions that it may be gradually tilting its trajectory toward Earth. As it drew closer to the object, the James Webb Space Telescope recorded something no one dared to imagine inside 3I Atlas. A source of light appeared bearing unmistakable signs of being artificial. 3I Atlas did not begin with a roar, but with a whisper, a faint glimmer of light far away, well beyond Jupiter's orbit, almost indistinguishable from the background stars. Yet there was something about it that seemed to pulse. It was not the brightness itself that triggered the alert systems, but the way that brightness changed. Too smooth, too precise. This was control, stability. It did not follow any natural dust outburst model or rotational phase curve. It simply grew brighter, like a switch being turned on. Astronomers from Mauna Kea to Chile cross-checked the readings. Its trajectory was steep, cutting across the plane of the ecliptic at an unusual angle, yet it showed none of the thermal lag typically seen in interstellar objects. There was no coma, no visible tail, no outward jetting that could explain the increase in apparent magnitude. And still, night after night, the object gleamed more intensely. One spectral scan changed everything. Instead of the expected icy volatiles, the emissions hinted at reflective surfaces, metallic compounds. The light curve flattened, then surged, not a random flare, but a controlled acceleration of brightness at precise intervals, a signal. What was most disturbing wasn't what the telescopes saw, it was what they didn't. There were no rotational wobbles, no precession drift. The object was unnaturally stable, as if locked into a gyro-stabilized orientation. Every 11 minutes the same surface faced Earth, like it wanted to be seen, or worse, wanted to observe. Some proposed it was a shepherd fragment, a remnant of a larger body. Others whispered the term active probe cautiously. What kind of celestial body increases luminosity on schedule without heat, without outgassing? One question lingered in the cold silence of the observatories. If it wasn't responding to physics, what was it responding to? The surface was cold. In the visible spectrum, 3I Atlas revealed nothing but a dark matte silhouette, absorbing light rather than reflecting it. But in infrared it glowed. Initial thermal maps gathered from the Spitzer Legacy Array showed an anomalous internal heat signature. A localized emission point buried deep beneath the surface pulsed with a regularity that defied natural thermodynamics. Unlike solar-heated comets whose warmth gradually spreads across their nuclei, this object radiated from within steady, uniform artificial. Thermal inertia models failed to explain the persistence of heat. There were no signs of radiogenic decay, no evidence of tidal interaction. The object wasn't spinning fast enough to generate frictional heating, and yet its internal core maintained a temperature more stable than many moons of Saturn. Then came the angular scan from ESA's Gaia auxiliary optics. A hexagonal thermal boundary was detected geometrically sharp with emissive symmetry. This was not erosion, it was structure. Some compared the pattern to baffle shielding used in deep space probes to manage internal temperatures without visible exhaust. Others suggested a thermal sink array designed to emit waste heat directionally, possibly away from Earth. But for one brief interval during its nearest alignment with Mercury, the emission shifted and pointed directly at us. Engineered symmetry in nature is rare but not unheard of. The hexagonal storm at Saturn's pole, the crystalline structure of basalt columns. Yet this was no accident of turbulence or mineral formation. This was containment. Deliberate, intelligent containment. Could it be a reactor? A propulsion housing, or perhaps a shielding system masking a more delicate core? More troubling was the regularity of the signal itself. 11-minute cycles, each time releasing the same narrowband infrared pulse, fading gradually into thermal silence before re-emerging. This wasn't a dying object. It was breathing methodically, patiently, deliberately. To label such a thing as comet felt increasingly absurd. This wasn't a relic. It was a mechanism. And mechanisms, unlike meteoroids, are built at a distance of 2.3 AU as 3I Atlas passed the orbit of Mars. The Lucifer instrument array aboard the Large Binocular Telescope captured a reflected spectral anomaly, sharp angular returns in the near-infrared band. Not diffuse like ice, not granular like dust, but coherent, reflective. Surface analysis showed unmistakable signs of nickel-dominant alloy composition, but with ratios inconsistent with any known natural source. Iron, typically abundant in stellar debris, was nearly absent. Instead, the surface was laced with trace elements of vanadium, titanium, and rare earth metals in precise proportion. This was not cosmic randomness. This was selection. Purposeful material engineering. More revealing was the directionality of reflected light. Unlike comets or asteroids which scatter solar radiation broadly, 3I Atlas returned concentrated beams along narrow axes. These beams varied subtly every 11 minutes, matching the thermal pulse interval noted earlier. Together, the data painted a pattern heat from within reflected light without oscillating in sync. It was not illumination, it was transmission. One hypothesis emerged: the surface was layered with metamaterial films capable of manipulating photonic direction. Such technology, in theory, could serve two purposes: energy harvesting or signaling, or both. But signaling to whom? Another anomaly: polarization shifts. Ground-based polarimetry registered high degrees of linear polarization, far beyond what silicate, dust, or carbon-rich surfaces can produce. In laboratory settings, such readings only arise from structured lattice surfaces, akin to those found in photovoltaic arrays or stealth coatings. No signs of rotation-induced torque, no precession. It simply hovered through space, fixed in orientation like a lens calibrated towards some distant point, or a mirror waiting to be seen. By the time it crossed Earth's orbital path, the question had crystallized across observatories. This was not a remnant, it was a construct, and its silence was intentional. At first, the light seemed ordinary, just a narrow, persistent band in the near-infrared spectrum. But when researchers overlaid the readings from Webb Hubble and 3 ground-based observatories, they noticed something that stopped every conversation cold. The wavelength didn't drift. It didn't scatter. It didn't behave like reflected sunlight at all. Instead, it held steady inside a frequency window commonly used in terrestrial communication and guidance systems. That alone would have been strange. But then came the rhythm. Every 11 minutes, perfectly aligned with the thermal pulses noted earlier, the signal sharpened into a narrow spike rising above background noise with uncanny precision. No comet in recorded history has ever produced such periodicity. Natural processes fluctuate, vary, decay. This one repeated like a clock that knew it was being watched. Spectral decomposition revealed subharmonics within the band, tiny fluctuations too ordered to be random. Analysts described it as structured noise, the kind produced when an optical system transmits information too faint to decode but too deliberate to dismiss. Some likened it to early spacecraft beacon patterns, where a constant carrier wave masks embedded encrypted data. Others compared it to LED array modulation, a method used on Earth to send compressed signals across deep space without radio bleed. Still, the most unsettling discovery came from cross-correlation. When the pulses from 3 nights of observation were stacked, the intervals aligned with microsecond accuracy. Not even pulsars maintained such consistency without drift. Whatever was generating the emission wasn't reacting, it was following a program. And then the silence. The modulation never changed, never escalated, never responded. It was as if 3I Atlas wasn't sending the message to us at all. It was broadcasting to someone else, someone who might have already heard it. It was Avi Loeb who first posed the uncomfortable question aloud: what if it's not here to pass by, but to collect? The energy output of 3I Atlas wasn't just an anomaly, it was a contradiction. At 2.1 AU, solar flux should have been too weak to power sustained internal activity. Yet the object maintained stable thermal emissions, periodic light modulation, and a temperature gradient that suggested continuous energy regulation. but from where one possibility: inductive harvesting. Several instruments detected minor fluctuations in the local interplanetary magnetic field, subtle rhythmic pulses that aligned with 3I Atlas's rotation cycles. In theory, a superconductive coil travelling through solar wind could generate energy via magnetic induction, just as Earth's satellites use passive charge collectors. But 3I's Atlas wasn't reacting like a passive object. It was synchronizing, matching field shifts, timing its pulses, drawing energy not by chance but by design. ESA's solar orbiter captured something else: localized shifts in solar plasma density trailing behind the object like a wake. Not gravitational, not turbulent, organized. It resembled a magnetic funnel redirecting solar particles into a converging path precisely toward the object's rear axis. What kind of propulsion requires plasma capture and magnetic scaffolding? More alarmingly, the energy absorption appeared selective. It ignored background particles. It targeted high-energy protons, as if filtering, as if refining. Was this a comet collecting heat, or a system harvesting fuel? No threat posture was visible, no acceleration toward Earth, no active emission toward satellites. But silence is not absence. Stability is not peace. Some began to suggest it was a solar scavenger, part of a network, not a lone visitor, a relay, a siphon. And if that were true, then the next question wasn't what is it doing, it was, how many more are already here? When 3I Atlas crossed the orbital plane of Earth, astronomers expected a gentle, predictable arc following the hyperbolic trajectory it had displayed for months. But the numbers didn't hold. JPL's trajectory solution was off, not by much, just 0.0007 degrees, but at interplanetary scale that meant thousands of kilometers, enough to miss a planetary intercept, enough to intentionally avoid something. Over the course of 4 days, that deviation increased. Observatories in Chile, South Korea, and New Mexico confirmed a subtle, non-gravitational acceleration vector, curving gently sunward counter to standard outgassing forces seen in comets. There was no coma, no jets, no trailing ice, and yet the object was adjusting course. That's when the brightness spike hit. Within a single observation window, its apparent magnitude jumped by 1, 6, an increase too fast and too clean to be natural reflectivity. There was no flare, no debris, no light echo, just a sudden unwavering intensity focused in a narrow vector. It wasn't random reflection, it was aim. Infrared channels showed no temperature spike, meaning the brightness was not due to heat. It was coherent, spectrally narrow polarized. In other words, signal light. The timing matched the moment of its directional shift. 1 frame before the curve began, the object flared, then stabilized, then dimmed. 1 pulse, 1 pivot. For some, this marked the turning point. No longer just anomalous 3I Atlas had made a decision. Upon closer spectral review, a peculiar pattern emerged in the reflection curves of 3I Atlas. The surface did not simply reflect light, it responded to it. Under solar flare exposure, instead of heating uniformly, certain regions of the object's outer shell shifted reflectivity in real time, modulating albedo with near millisecond latency. That's not thermal inertia, that's active control. Material scientists from ESA compared the readings to adaptive metasurfaces, exotic compounds capable of reconfiguring their optical properties under electromagnetic influence. On Earth, such materials exist only in lab-scale prototypes, mostly for cloaking applications or directional beam steering. Yet 3 Atlas exhibited a full-body photonic shift during a Class B solar event. Its reflective profile adapted, absorbed, then returned to baseline. There was no energy burst, no visible mechanism, just a silent transition as if it anticipated the flare. What kind of material adapts to solar radiation without delay and to such precision? More curiously, radio quiet zones were detected in a 300-meter radius during those transitions. Temporary radio silence, as if some kind of local dampening field came online. No signal escaped, no interference entered. The object seemed to cocoon itself briefly, then resume normality. If this was engineering, it was not primitive. If this was shielding, it was not for us. There is perhaps no deeper silence than a machine that knows when not to be heard. 3 Atlas had entered the constant observation grid of the International Asteroid Warning Network, a globally coordinated body tracking near-Earth objects with shared data protocols. Their mission: early warning, not interpretation. But even within their cautious language, something changed. Yorn's internal bulletin marked 3I Atlas with a rare classification tag deviodynamic vector outlier. Only 4 objects in history have ever received this tag, all of them eventually reclassified as defunct hardware or unmodeled debris. But 3I Atlas didn't fit that profile. Its trajectory was clean, stable, but somehow wrong. At 1.94 AU, the object's projected perihelion shifted by 0.06 AU over a 72-hour window. That's not normal drift. That's a delta of nearly 900,000 kilometers unexplainable by solar pressure, planetary perturbation or cometary outgassing, because again, there was no coma. Cross comparisons with the Pan-STARRS archive showed something even more disconcerting. The divergence began not gradually but abruptly on the same timestamp as the last coherent light pulse, detected 2 weeks earlier. Like a command had been received, or a phase had completed. Yorn teams in Tokyo and Rome issued separate anomaly reports noting a non-ballistic signature. The deviation wasn't due to external forces, but an internal decision tree, a switch from passive drift to programmed course. And for the first time, ILN's secure back-end channel was activated, a protocol used only for non-nuclear international coordination in case of threat. Not to alarm the public, not yet, but to prepare infrastructure scenarios if further divergence occurred. Because the truth was clear to those tracking it second by second, 3I Atlas wasn't just passing through, it was adjusting. It was aware of the system it was moving through, and it was choosing its path with knowledge of what lay ahead. The Subaru telescope in Hawaii picked up a subtle aberration. 3I Atlas's velocity vector was no longer strictly radial. A lateral component had emerged side-slip motion that defied gravitational expectations. Initial skepticism blamed parallax distortion, but dual confirmation from both the Very Large Telescope in Chile and the Goldstone Radar Array removed all doubt. The object's drift was real, and it was lateral across its own orbital path, not along it. Measured offset 2.7 km per hour, consistent and stable over a 14-hour window. There is no known natural force that can produce controlled transverse movement in interstellar objects without chaotic rotation or significant mass ejection. 3I Atlas exhibited neither. Its angular momentum was steady. No tail, no thrust bloom, no detectable venting. And yet, it slid sideways. Smoothly. Deliberately. That same day, deep infrared from JAXA's Akari array showed microsurges in thermal symmetry, minor pulse-like temperature spikes centered along the object's flanks. The pattern resembled reaction control systems seen in orbital platforms. Heat, wait, heat again, but with no visible exhaust. Which raised a chilling question: was 3I Atlas correcting itself? Orbital analysis conducted by the Korean Astronomy and Space Science Institute revealed a precise alignment maneuver. The object adjusted its orientation to recenter along a solar magnetic boundary, a Parker spiral corridor used primarily by spacecraft for efficient travel along the sun's rotational field. This was not adaptation, this was navigation. Speculation grew in classified briefings. Some scientists floated the term inertial nullification nodes, hypothetical tech that cancels momentum locally. Others whispered about magnetogravitic slipstreaming, once pure theory, now uncomfortably close to observation. Whatever the method, the effect was undeniable. 3 Atlas was not following the laws of motion. It was rewriting them locally, and every shift hinted at an intelligence responding to something unseen. At 2.1 AU from the Sun, just days before crossing Mars's orbital plane, 3I Atlas executed a maneuver that defied passive physics. Without gravitational assist, without known external force, the object's velocity increased by 4.2 meters per second, and its angle relative to the ecliptic plane tilted by 0.03 degrees. Small shifts, but ones that required energy. Detectable energy. The Deep Space Network flagged the anomaly first. Then came corroboration from ESA's Gaia tracker, which confirmed a non-gravitational acceleration vector emerging perpendicular to solar influence. The curve wasn't chaotic. It followed a Bezier-like arc, the kind seen in human flight simulations, smooth, anticipatory, pre-modelled. What could cause such a motion? No cometary thrust signature, no venting, no particulate emissions. But a narrow-band thermal signature was detected trailing the path, a coherent directed wake, in the far infrared band, decaying in a logarithmic curve indicative of structured dissipation, not random heat. Engineers studying deep space propulsion saw something disturbingly familiar. They called it field drift residue, theoretical residue from a form of inertial redirection. Think of it not as thrust, but as permission to fall differently. A controlled imbalance between internal mass and external momentum. It matched no known drive system, but aligned partially with early-stage concepts from electromagnetic asymmetry propulsion. The trajectory was now clearly being shaped, not inherited, and the precision of it suggested intention. No wobble, no feedback overshoot, no oscillation. It was a flawless vector application, like an autonomous system with millisecond predictive correction. More unsettling was the silence. No radio burst, no beacon. Nothing to identify the actor behind the motion. Just motion itself, as if the method, the silence, was the message. If this was propulsion, it was not made for spectacle, it was made to pass unseen, and yet now all eyes were watching. As 3 Atlas left the orbital vicinity of Mars, observers expected a gentle drift outward, perhaps a slow loop through the asteroid belt. Instead, it began a broad, deliberate curve, one that aligned not with planetary gravity, but with the heliospheric current sheet itself. A magnetic boundary, a charged corridor. At first the shift looked like mere trajectory fine-tuning, but spectrometric scans from the solar orbiter revealed something far more profound. A spinning asymmetry in ionized particle fields around the object. Thin, pulsing arcs of accelerated plasma bending inward, not outward from the solar wind. Like paddles dipped into a stream, redirecting flow. Researchers at JPL proposed the unthinkable. 3I Atlas was using the plasma environment itself as fuel, as force, as framework. A magnetohydrodynamic MHD drive, once considered science fiction, was now the only viable model. Unlike traditional propulsion, an MHD drive extracts momentum from electromagnetic fields, no exhaust, no mass loss. Just a dance of ions channeled through precisely modulated magnetic coils. In Earth-based labs, such drives have moved testcraft a few centimeters, but 3I Atlas was performing the same trick across millions of kilometers. Every pulse of redirected plasma created a torque, and that torque steadily turned the object, not toward deep space, not toward the outer Kuiper arc, but toward Jupiter. The trajectory shift wasn't random. It bent toward a gravitational node, a Lagrange point in the Jovian system, known to house stable energetic fields and dust mass accumulations. These regions are ideal collection zones where probes could harvest particles, study radiation, or recharge. Yorn's emergency response team quietly flagged this as a strategic acceleration event. The term was clinical, the implications were not. For something to aim that precisely from that far using field-based propulsion, it must understand the invisible scaffolding of the solar system. It must know more than we do. And if it was heading toward Jupiter, the question was no longer why is it here, but rather what has it come to meet? AAT-03-12, UTC multiple deep space tracking arrays, DSN Canberra, ESA's Cebrero station, and JAXA's Yasuda antenna simultaneously registered signal loss. Not from 3I Atlas directly, but from probes in its projected path. 2 Mars-orbiting satellites and a trailing CubeSat relay launched for spectral data collection all went silent within a 12-minute window. There was no hardware malfunction, no radiation burst, no known solar event. Just silence. A coordinated, synchronized absence. But exactly 38 minutes later, a pulse returned not from the satellites themselves, but from behind 3I Atlas's position. The signal was faint, non-modulated, a low-frequency broadband sweep cycling in descending pitch. At first, it resembled a passive radar reflection, but when JPL analysts compared its phase signature to prior broadcasts, they found something chilling. The echo wasn't a repeat of the last signal. It was a compressed spectral inversion, as if someone or something had received the original message, encoded it, then played it back in reverse, as a response. This wasn't distortion. This was deliberate mimicry. And it was timed to arrive after the blackout like an acknowledgement, a nod. Scientists proposed benign theories, plasma lensing field phase scattering complex signal diffraction through MHD plasma wakes. But none explained the timing, or the structured inversion, or the eerie regularity of the down-pitched pulse intervals, each precisely 11.37 seconds apart. That interval matched a curious data point, the thermal pulse cycle from the object's prior emissions, a rhythm believed to be tied to its internal systems. Was the signal tied to that pulse, or worse, was it produced by it? Theories fragmented. Some called it a communication probe, others warned of active scanning. A few even suggested a form of cognitive echo where data is not simply relayed but interpreted, altered, and returned with embedded metadata. The CubeSat never came back online. The Mars relays eventually reconnected, but with timestamp gaps missing precisely the moments when 3i Atlas passed between them, and in that blank space where telemetry should have been was only the echo, still repeating, still shifting, as if listening for a reply. Yorn released an encrypted trajectory update to its global partners. Embedded deep in the orbital data was an anomaly not tied to current motion, but to a projected resonance, a coordinated intersection not with a planet but with a time point. At 0.97 AU from Earth's orbital path, the object's adjusted trajectory intersected a rare nodal crosslink, a transient position where Earth, Moon and Sun form a gravitational aperture. This configuration, occurring only once every 41.3 years, creates a brief period where low-thrust vectors can return an object to Earth with minimal energy cost. The problem: this maneuver requires advanced temporal modelling accounting for gravitational lag, solar flux density and planetary magnetic bleed. Even with our best simulations predicting, it requires continuous recalibration. Yet 3i Atlas had already adjusted its course 2 days before the aperture's forecasted alignment was made public. The implication: it had prior knowledge of our orbital harmonics. Or worse, it was responding to a pre-existing mission schedule, a mission to come back. Cross-reference with long-range data showed something even stranger. The projected Earth flyby wasn't just passing through it, curved into an aerobraking corridor, a maneuver used by returning spacecraft to reduce speed by dipping into Earth's upper atmosphere. But 3 Atlas isn't built for heat shielding. It lacks spin rate compensation. It shows no radiation deflection flare that a comet typically exhibits when encountering Earth's exosphere. Instead, its body temperature had begun rising slowly, not from solar exposure but from within. An internal energy build-up consistent with a staging sequence. IEAW and analysts broke protocol and issued a preliminary classification, Potential Controlled Return Object PCRO. This was no longer a passive flyby, it was a navigated return. But to what end? To observe Earth again, to release something into our orbit, or to rendezvous with something that's already here? The last data line from the orbital simulator showed a chilling coincidence. The planned periapsis of the return matched the coordinates of Earth's geostationary ring right above the Pacific, where dozens of classified military and telecom satellites orbit in silence. Not a crash, not a landing, a dock. On December 9th, just hours after the object exited Mars's orbital domain, NASA's Near-Earth Object Observation Program logged something no model could rationally predict: a non-inertial velocity spike. The object had accelerated. Not gradually, not through planetary gravity, but via a burst, a measurable delta V of 6.8 ITS/ms recorded over just 47 seconds. No comet does that. No asteroid can. The trajectory shift violated Newton's first law. No known force accounted for it. No gravitational slingshot, no detectable mass ejection, no radiation surge. Just motion without interaction. This is where physics breaks, or something else bends it. Spectrometers aboard the ESA's Lagrange solar monitor detected a localized drop in interstellar plasma density, like a temporary bubble formed around the object. Not ionized, not explosive, just missing mass. A silence in the medium. Physicists coined it the null-wake effect, a theoretical displacement field where resistance vanishes temporarily. The only viable analog experimental results from high-intensity magnetofluidic chambers where rotating plasma fields distort inertial frames on microscales. But this wasn't micro, it was interplanetary. The data suggests the object is not resisting the laws of physics, it's repositioning them. Instead of pushing against space, it's slipping through it like a boat adjusting the water itself rather than rowing harder. A vector realignment that doesn't fight gravity but briefly erases its grip. The implications are enormous. If this is a form of inertial dampening or space-time manipulation, it represents post-Einsteinian engineering, a form of technology so advanced it doesn't break our laws, it makes them irrelevant. And as Earth becomes the object's next target vector, the question shifts. Is this maneuver for speed, or for arrival timing? What's more dangerous, a fast approach or a perfectly calculated one? Using synchronized baselines from 5 independent observatories, including ALMA in Chile and the submillimeter array in Hawaii, a consensus image of 3i Atlas was reconstructed frame by frame, mass by mass. Over a 12-day tracking interval, one constant began to dissolve. The object was getting lighter. At first telemetry noise was blamed, then thermal expansion, then gravitational shear. But no theory held when cross-validated with infrared scatter modelling. 3I Atlas had shed nearly 2.6% of its total mass, without visible fragmentation, no ejection plume and no trailing debris field. No known cometary behaviour matched it. In comparison, when Oumuamua passed through the inner solar system, its negligible outgassing still produced microacceleration. With 3 Atlas, however, there was measurable mass loss, but without any associated kinetic recoil. Mass vanished. Momentum didn't respond, like something was peeling itself away. Radar echoes confirmed the perimeter envelope had subtly shrunk, not eroded, but restructured. Its radar cross-section narrowed by 4.2%, not in chaotic melt, but in precise inward fold patterns, as if a shell had retracted, exposing an internal lattice. What kind of object loses mass without force? What structure can shed material without spin imbalance? A new hypothesis surfaced: intentional mass shedding. Not waste, but offload. Not breakdown, but preparation. A morphing architecture. If true, this wasn't a body under stress. It was a vehicle undergoing configuration shift, compressing, perhaps priming a new operational mode. The loss of material wasn't failure. It was part of a sequence. But what phase comes next? If a vessel lightens itself, it may be preparing for entry, or for release. And if we can't track what it lost, we may not notice what it leaves behind. Spectroscopic analysis from the James Webb Space Telescope provided the most detailed compositional scan of 3I Atlas to date. What it revealed overturned every assumption. The object's surface reflected an atypical absorption curve lacking the silicate and volatile signatures of comets. Instead, it showed layered metallic compounds including titanium carbide complexes, beryllium inclusions, and most puzzling, isotopically pure molybdenum. On Earth, such purity requires industrial refining. But here it was suspended in the vacuum of space, perfectly aligned across a surface band. More than just exotic, the structure appeared engineered. Elemental layering followed a periodic micropattern. Nanoscopic ridges and recesses repeated every 32.8 microns, far too regular for natural crystallization. These formations reflected wavelength-specific infrared, allowing the object to radiate internal heat at a regulated pace. And yet internal temperature never exceeded 86 Kelvin, even during its closest solar approach, a value impossibly low without active regulation. This was not passive cooling, it was thermal containment. Using deep-field thermal interferometry, researchers mapped an internal cold core surrounded by multiple shells, each acting as phase-shifting layers. As solar intensity rose, outer layers adapted reflectivity, preventing conduction inward. It operated like a nested thermal diode, maintaining a heat vacuum within. Why maintain such cold? What needs to stay frozen that close to the sun? Some proposed the idea of quantum material states of matter that collapse or decohere when exposed to thermal noise. Others pointed to hibernation systems where data machinery, or even consciousness, could remain preserved across interstellar distances. But the truth may be darker, because this kind of stability isn't just for protection. It's for activation. The object wasn't shielding itself from the sun. It was waiting for the precise moment the vacuum, the heat, the radiation all align. And when they do, the metal will remember what it was made for. At first glance, the motion of 3I Atlas seemed erratic, slight coarse bends, velocity pulses, periodic luminosity spikes. But when overlaid across a solar system model and adjusted for barycentric influence, a sobering pattern emerged. The object wasn't drifting, it was choosing. NASA's JPL team ran 100,000 Monte Carlo simulations, factoring gravitational well solar wind flux, Yarkovsky effect variations, and three-body perturbations. In none of them, did a natural object follow the path that 3I Atlas traced. Not with that timing, not with that precision. The calculated probability of such a trajectory occurring without intent was less than 0.047%. It didn't just pass near Mars, it synchronized its acceleration burst just as Mars's magnetotail aligned with Earth's orbital plane, creating a temporary low-resistance plasma corridor. A gravitational fluke or an engineered slingshot. Further statistical clustering showed that its approach vectors deliberately avoided resonant disruption zones, the very pockets of instability where comets often fragment. In other words, it was navigating around chaos, not through it. But the most haunting probability calculation came from the ESA's Deep Space Triangulation Array. The object's trajectory brings it within 0.008 AU of Earth's orbital path not once but twice within a span of 41 days. A double approach, with maximum visibility gaps during both passes. Probability of that being random 0.0002%. The numbers don't scream, they whisper. They whisper that this isn't noise, it's signal, not mistake, but message. When entropy is this selective, when chaos curves into coherence, the universe stops being the speaker and becomes the receiver. The question no longer is what is it, but rather why is it trying to be seen and by whom? Because if these probabilities hold, then nature didn't roll the dice, something loaded them. By the midpoint of its trajectory toward perihelion, 3I Atlas had shed more than assumptions, it had shed trust. No known comet behaves this way. No asteroid travels with such selective coherence, and no natural body maintains a uniform surface temperature while undergoing course-corrected deceleration. One unsettling hypothesis began to rise from the margins. What if it was never a comet to begin with? Enter the probe camouflage theory, first proposed by a small group at the Max Planck Institute and independently mirrored by the Planetary Science Unit at Kyoto. The model suggests 3I Atlas is not merely an object passing through our system, but a cloaked interstellar probe operating under deliberate disguise protocols. The theory rests on 5 pillars. Thermal masking, surface readings remain below 90 Kelvin, even under solar heating, mimicking dead mass, while internally retaining complex thermal management. Trajectory mimicry. Its orbit mimics long-period comet arcs, but with micro-adjustments at key gravitational nodes, subtle enough to avoid early detection, precise enough to suggest navigation, material misdirection. Spectral readings suggest a composition similar to cometary bodies, but with ultra-pure metallic veins, isotopic anomalies and pattern-locked crystalline formations, materials associated more with design than detritus. Signal management. Its brief thermal pulses occur in Fibonacci rhythm, a frequency not known to arise naturally, but often favoured in artificial communication design due to its mathematical balance and compression efficiency. Predictive silence. It approaches during observational blind zones, exploiting both solar alignment and instrumental limitations, not avoiding detection, but controlling the narrative of its appearance. If true, then this isn't our first contact, it's our first observation of being observed. The implications stretch beyond astronomy, they pierce into intent, because a probe disguised as debris implies a strategy, one of stealth surveillance and possibly assessment. We were not the ones scanning the skies, we were the ones being scanned, and perhaps we were meant to notice, but only once it was already too late to stop watching back. In late-stage tracking data from both the Deep Space Network and ESA's STR-MICS array, something impossible appeared in the Delta V logs. 3I Atlas was accelerating in measurable bursts without ejecting mass. No plume, no outgassing trail, no thermal signature of expulsion. Cometary bodies typically alter their velocity through volatile release jets of gas and dust as they heat under solar radiation. But 3I Atlas exhibited no rotational spin variation, no sublimation spikes, and no directional debris fields. Instead, its motion reflected clean vector-aligned thrust, almost surgical in profile. This was not a slingshot. This was applied force without reaction mass. Engineers from Caltech attempted to reconstruct the anomaly under known propulsion models. Solar sail, no, there was no surface flare, no deviation from incident light patterns. Magnetic drive, unlikely, no measurable interaction with the solar wind. Nuclear microburst, no gamma traces, no shielding bloom, no evidence of heat asymmetry. What remained was a theory both elegant and disconcerting: field propulsion, manipulating local spacetime curvature, or plasma inertia without traditional fuel mechanics. A method long hypothesized but never demonstrated at planetary scale. And yet here it was, a push with no pushback, a leap without legs. Physicist Adil Khoury phrased it bluntly: if this is propulsion, then it doesn't want to go fast, it wants to go quiet. Because when a craft leaves no trail, or it leaves no target. Perhaps 3I Atlas wasn't fleeing, perhaps it was positioning, quietly, efficiently, beyond our reach yet fully within our sight. After months of analysis, calibration and independent peer review, the international consortium released its final report on 3I Atlas. It did not offer certainty. It offered something far more unsettling: a pattern without a cause. Every anomaly, thermal pulses, mass-shedding non-ballistic motion, and silent propulsion was confirmed by at least 3 independent arrays. No known astrophysical or engineering model within the limits of current human knowledge could account for all variables simultaneously. And so, the final summary adopted a phrase rarely seen in scientific documentation. The object's behaviour exceeds the explanatory scope of natural origin models. No definitive label, no claim of extraterrestrial design, just the quiet admission that something doesn't fit. The object now receding toward Jupiter's orbit has dimmed. Its surface reflectivity has decreased by 82%. Its emission pattern is silent, as if it had finished its transmission, or completed its scan. IO1, NASA, and JAXA have ceased active tracking. Not because the anomaly ended, but because the window of observation has. What remains is the data and the doubt, because in that doubt lies a shift from what is it to why was it here. The final conclusion isn't a statement, it's a question left deliberately open. If we were being observed, then what did we just reveal? Not a threat, not a message, but a mirror cast through space, drifted through time, and now slipping back into the dark. We saw it saw us, and neither will remain unchanged. It didn't end with a message, it ended with silence, but not the silence of absence, rather the silence of something that had completed its purpose. 3I Atlas came and went like a calculated breath through the cosmos, not fast, not chaotic, not random. It adjusted its trajectory. It changed its brightness. It pulsed in heat without fire and moved without mass. Every action felt chosen. And in that intent we saw not a comet, but a question. What visits and hides its trail, what observes and then fades. The scientists gave us data, heat curves, spectral maps, delta V logs. But beneath the numbers, something deeper lingered, a sense that we'd been watched, measured, perhaps even weighed. No alarms were raised, no conclusions declared, only shifting protocols and quiet recalibrations in the deep space networks. Because this wasn't about fear, it was about realization. Something came close enough for us to notice, and then disappeared before we could understand. And maybe that was the message, not a threat, not a greeting. But a mirror tilted ever so slightly, revealing how little we truly know. So now we look at the stars differently. We listen harder, and we wonder if we were being observed. What did we reveal? What did it learn? And will it ever return, not to speak, but to see what has changed? We often think of first contact as something loud, an arrival, a landing, a message. But what if it begins in silence? What if the first encounter is not an event but a calibration? A distant intelligence might not announce itself with lights and language. It might begin with presence, with quiet proximity, with watching. And if 3I Atlas was not a natural object, then maybe it was the first step of a process we barely recognize. It didn't communicate in words, it didn't break our skies, it simply passed by, deliberately. And in doing so, it may have measured something we don't yet know how to quantify: our awareness, our readiness, our curiosity. Because if they are advanced, truly advanced, they don't need to ask us anything. They only need to see how we respond to mystery, to pattern, to anomaly. Perhaps this wasn't a mission of contact. Perhaps it was a probe of potential. Think about the timing. It arrived when our instruments were precise enough to notice small deviations, when our global networks were fast enough to compare anomalies, when our scientific community was just open enough to consider the unexplainable without ridicule, and then after a brief interaction with our senses, our minds, our imaginations, it left. But departure is not the end. Not if it was watching, not if it was listening, and not if it left behind questions instead of answers. Because now everything has changed. Every new object will be analysed differently. Every anomaly will carry the weight of possibility. We've become aware not just of the object, but of our own limited perspective. That alone may have been the goal. The next phase might not come tomorrow, or next year. It may take decades, or it might already be unfolding in data we haven't looked at closely enough. But whatever happens, we've passed a threshold not in technology but in perception. We looked up, we noticed, we asked the right questions, and somewhere perhaps far beyond our reach, something or someone took note of that. If this was a test, then perhaps we just passed the first layer. A civilization capable of sending such an object wouldn't rely on spectacle. It wouldn't need to land or interrupt our systems. It would use patience, precision, and presence. The kind of presence that doesn't demand attention but quietly studies our reaction to the unexplained. How we argue, how we doubt, how we theorize. Maybe 3i Atlas was never meant to change the world in an instant. Maybe it was meant to tilt our perspective just slightly, to fracture the illusion that we understand everything in the sky. Because once that fracture exists, it grows, and when curiosity spreads, preparation begins. We're mapping more, watching, closer coordinating faster. Not because we were told to, but because something made us feel watched. That feeling is powerful. It lingers. It creates a kind of quiet momentum across generations. A ripple in our scientific trajectory that may lead decades from now to real readiness. And when the next anomaly comes, and it will, we may not be as blind. We may not be as dismissive. We may not need proof to start preparing. Because the message was never, they are here. The message was, they have eyes. There are moments in history that don't feel like history when they happen. They feel small, quiet, almost forgettable. A signal lost in noise, a shadow across a lens, a temperature spike without explanation. But sometimes those moments are the ones that echo the longest, not because they were dramatic, but because they were the first thread of a larger design, one we're only beginning to see. 3 Atlas may be gone, the sensors have gone silent, the data logs have closed, but our questions remain open, and that may be the point. Because long after the object fades from memory, the doubt it left behind will continue to shape how we see the sky. We're not just scanning for asteroids anymore, we're scanning for intent. And somewhere beyond light years, that may have been the first step they were waiting for.